Good morning, everyone. I'm Aasha G, and I welcome you to the presentation about numerical simulation flow over NACA0012 aerofoil pitching at low frequencies. This work has been carried out by students of the Department of Mechanical Engineering in B.M.S College of Engineering under the guidance of Professor Ramesh Kolur and Professor Ramesh M. Chalkapur. This presentation is a brief overview of our work over this past year, containing our motivation, problem definition, SU2 modeling, numerics, geometry and mesh, grid and time-independent study, Openfoam solver setup, results, and conclusion. Our motivation to work on this topic stems from the fact that there is a large number of aerial and underwater vehicles and their components that undergo oscillatory motion. For example, submarines, autonomous underwater vehicles, and their components in shallow water. We decided to focus mainly on the pitching aspect. Fluid flow is the relative low frequency oscillation component, and the flow can be considered quasi-steady. Flow at low speeds approaching the aerofoil is incompressible. Our objective is to conduct numerical analysis over the pitching NACA0012 aerofoil using two open source CFD platforms, that is SU2 and Openfoam, and also to compare results obtained from both softwares. Coming to the problem definition, the following criteria outline the premise of the present study. The knowledge about varying pressure distribution is essential in accurately predicting and designing the performance of aerial and underwater vehicles and their components, as they form a crucial part in the stability of the vehicle and are affected by the pitching motion. The pitching motion can be of the form alpha of t is equal to alpha naught plus alpha a sine omega t, where alpha is the angle of attack in degrees varying with time. Alpha naught is the mean angle of attack about which the aerofoil oscillates in degrees. Alpha A is the amplitude of oscillation in degrees. Omega is the frequency of oscillation in radians per second, and T is time in seconds. The static simulations are done for various angle of attacks varying from -9 degrees to +9 degrees. Some of the flow parameters are shown below. The solver used in SU2 is the incompressible RANS solver and pimple foam in Openfoam. Turbulence modeling is done using Mentor's SST, and aerodynamic coefficients like drag and lift coefficients are analyzed. Grid-independent study is also carried out. Static and dynamic simulation results from both SU2 and Openfoam are compared for various angle of attacks. The flexible class structure of SU2 enables the modeling of CFD problems in 3 dimensions. SU2 provides various solvers that can solve the incompressible as well as compressible forms of Euler, Navier-Stokes, and Reynolds average Navier-Stokes equations. The incompressible RANS solver is chosen for the current numerical analysis, and it solves the incompressible Reynolds average Navier-Stokes equation. The partial differentiation form of this equation is shown here, where V is the vector of working variables within the incompressible RANS solver, Fc is the vector of convective fluxes, Fv is the vector of viscous fluxes, and Q is the source term. As the current study deals with the flow of velocities of Mach 0.1, the flow is modeled as incompressible, implying that the density does not vary with time. Hence, to link the continuity and momentum equations and solve incompressible Navier-Stokes equations in a fully coupled manner, SU2 implements Corin's artificial compressibility method. This method solves the governing equation of the formula shown. As the temperature variations for the physical situation being modeled are expected to be insignificant, the density is assumed to be independent of temperature. Hence, constant density model is chosen for the current analysis. Moving on to turbulence modeling. With the Reynolds number of the physical situation under study being in the transition region, turbulence modeling has been implemented through Mentor's shear stress transport model, SST model. Modeling of viscosity under turbulent conditions is achieved by the principle of Bosniak's hypothesis. Thus, viscosity mu is dissolved into dynamic and turbulent components. Mu d, that is the dynamic viscosity, is chosen constant for the current case as it is constant temperature flow analysis. Mu t, the turbulent component of viscosity, is computed using the SST model. SU2 also offers a one equation SA model. However, studies have generally concluded SST to be better suited for turbulence modeling. The Mentor SST turbulence model is an extensively used two-equation eddy viscosity turbulence model that combines K omega and K epsilon turbulence models. It implements K omega model in the boundary layer region and switches to the K epsilon in the region of free shear flow. It overcomes the sensitivity of K omega model to the values of omega and the free stream while also having better boundary layer modeling capabilities.
Coming to the numerics part in SU2, finite volume method is implemented by the SU2 solver for discretization of the governing equations. Median dual control volumes are constructed for the purpose of calculation of convective and viscous fluxes. As shown in the figure, such a volume is formed by connecting centroids, face, and edge midpoint of all the cells sharing a particular node in the primal mesh. SU2 provides a number of central and upwind convective schemes for both compressible and incompressible flows. For the current case, an incompressible upwind scheme available within SU2, which is flux difference splitting scheme, is selected. We have selected the upwind scheme as they are supposed to give higher order of accuracy over corresponding central schemes. FTS averages convective flux vectors on face of median dual control volume from values at nodes on either side of the control volume. The discretization thus obtained is first order accurate in space. Additionally, monotone upstream centered schemes for conservation laws MUSCL approach is employed to achieve accuracy in second order. To evaluate the viscous fluxes, the flow variables are averaged at the cell face of the control volume and the gradients are calculated. Green-Gus method is used for this purpose. Here, Green-Gus method is picked over the alternatively available least squares method because it is observed to perform better in the simulation of aerodynamic boundary layer flows over curved surfaces. After spatial discretization, a time discretization is performed. In the static analysis case, implicit Euler scheme is selected for the same. This scheme offers stability over a wider range of CFL numbers and is also capable of effectively handling CFL numbers much larger than 1. Local time stepping is implemented in SU2, which accelerates the convergence by allowing each cell in the mesh to advance at a different local time step. The option iter in the configuration file is used to control the number of iterations and can be alternatively controlled by the convergence criteria. To enable the dynamic analysis case, time domain is set to yes, which is set to no for the static analysis case, and a time marching method is selected. We have employed dual time stepping second order method for the same, which solves the equation given in the equation number 6 and involves real and fictitious time. The unsteady problem is transferred into a steady state problem at each physical time step and is solved as a steady state problem in this method. The pseudo-time iterations or the internal iterations are the iterations within each time step and are controlled by the convergence criteria. They can be alternatively controlled by using inner iter option in the configuration file. And the physical time iterations are the external iterations which control the total time of the simulation. The time step is controlled by using time step option in the configuration file, and the option max time controls the physical time. The total frames are based on the value of max time and the value of time step given. For the current case, we have employed a time step of 0.11 seconds and run the simulation for 7 cycles, where each cycle was of 40 seconds. A linear solver lies at the very core of any iterative procedure that involves a linear equation. Hence, selection of the linear solver is crucial to the effectiveness of the simulation in terms of accuracy, time, as well as memory. SU2 code offers a number of linear solvers, of which we have selected the flexible generalized minimum residual FGM-RES linear solver. GMRES solver is basically a very fundamental Krylov subspace solver. It provides a simple and efficient option to begin with. And FGM-RES is said to make the GM-RES more flexible and effective while keeping the implementation simple. Hence, it was chosen for the current study. However, in the future analysis, we intend to work on employing more efficient solvers available in the software. To improve the convergence rate of the linear solver used, preconditioning has been done using line-led preconditioner. As the mesh used for the simulation has highly stretched elements at a few locations, and line-led preconditioner is found to have reduced the number of preconditioning conjugate gradient iterations in comparison to the other common preconditioner, we have chosen line-led preconditioner for the current case. For our current study, the standard C-grid 2D structured mesh as shown in the figure has been used, which is available on GitHub repository of the SU2 Foundation. The grid we have selected has a far-field extension of 500 times the chord length with 57,824 points overall and 256 points on the airfoil. SU2-DEF function is then applied to reduce the unit chord length of the original mesh to 0.15 meter chord to fit the purpose of our simulation. The grid is stretched in the direction normal to wall with dense meshing provided around the airfoil to accurately model the parameters and the gradient in the proximity of the airfoil surface. The boundaries of the mesh, which are recognized as markers in SU2, are tagged as airfoil and far field, indicating the airfoil surface and far field boundaries respectively. To enforce the adiabatic no-slip wall condition on airfoil, constant heat flux boundary condition with zero heat flux is implemented on the airfoil surface, and far field boundary condition is applied on the far field to enforce free stream values on the far field. To obtain the pitching motion of the airfoil as required for the current analysis, volumetric deformation procedure is used. To do so, we have assigned deformation as value to the surface motion option in the configuration file. The mesh movement is based on a classical spring method where the stiffness matrix connects two ends of a single mesh edge and equilibrium of forces is obtained at each mesh node to accommodate the change. Here, first the airfoil is moved, followed by the deformation of the mesh to accommodate the new surface position for each time step. These are the captures at 0 and 9 degree angles of attack. To minimize the computational cost without compromising the accuracy of the solution, and hence ensure optimum utilization of resources, grid and time-independent studies were carried out in SU2. A grid-independent study was done on 3 progressively finer grids as listed here on static case under the same flow conditions with the same numerical algorithms employed. The mesh description and the corresponding lift and drag coefficients are as tabulated. We can see that the lift coefficient does not show any significant change with variation in grid refineness, and as per drag coefficient is concerned, the value are close for mesh 2 and 3 and marginally different for mesh 1. Hence, it can be concluded that mesh 2 can be chosen without compromising the efficiency of the results. Similarly, time-independent study was conducted over the course of half cycle for dynamic case with 3 sample step sizes of 0.25 seconds, 0.11 seconds, and 0.05 seconds. The CL curves for all the 3 cases showed perfect agreement with each other, and the CD plots were seen to overlap for the most of the duration. Only the CD plot for the time step of 0.05 second showed slight deviations. Hence, time step of 0.11 second was chosen for dynamic analysis case in SU2, which translates to 10 frames for a change of 1 degree angle of attack.
So I'm going to be talking about the solvers and methodology that are implemented in Openfoam. And again, this is divided into static case analysis and dynamic case analysis. The static case analysis, the solver that is used to execute the simulation was Openfoam. Openfoam is an incompressible flow solver where the equations in the algorithm have the density and pressure couplings removed, as well as pressure and energy. So this gives a constraint on the pressure equation because there is no explicit equation for pressure. Hence, the way the algorithm solves to uh, compute pressure is by semi-discretizing the momentum equation and computing pressure and so on, unlike in SC2 where they use Corin's artificial compressibility. So Pisoform is used for transient cases and it allows for Coulomb number to be more than one. But in this case, we have made sure that the Coulomb number is less than one after every iteration, so that there is sufficient accuracy in the flow field. And so piece of work works on the basis of outer and inner characters, where the number of outer characters defines the outer iteration performed. This is like saying, and the number of times the system of equations in form of a matrix is computed, irrespective of the convergence of the solution, at least for static use. And in inner characters, like they determine the number of iterations required to compute the pressure field, and that's again based on the algorithm where pressure and velocity, the because of the momentum equation, that is the constraint on this pressure, and then a velocity is computed, then pressure is computed, and then that is used to recalculate velocity and so on. In case of dynamic case, the pitching airfoil simulation, the Pimple algorithm is used. Pimple is a combination of piso and simple, and it's a transient case no open form, just like piso form, but it allows for dynamic meshing. So it solves continuity and momentum equation, which is constrained Navier-Stokes equation for incompressible flows, and these again are solved as matrices and using in a iterative way, just as I told you, semi-discretizing momentum equation and computing velocity and pressure and so on. It's just like simple algorithm, but for each time step, where the outer characters are the iteration, and once it's converged, it move on to the next time step. For the dynamic meshing, we use displacement Laplacian methodology, which solves a Laplacian equation of diffusivity for the respective boundary condition, where the mesh points around the airfoil are computed and solved such that these points are morphed and the airfoil moves. And compared to other methods with the spring 6 degree of freedom rigid point motion solver, which as the literature suggested might lead to possible errors if the geometry is complex, if polyhedral cells are on the edges. So displacement Laplacian seemed like the better method to solve this particular simulation. Although computational effort and time were higher in this particular method compared to other methods. So the results for static case analysis were divided into three things. One, the velocity contours. Second, the streamlines. And third, the plots, the flow coefficients and pressure coefficient plots. So the velocity contour for different angles is shown, and the main difference that were observed between the two software was the flow at the leading edge, where there is slightly a higher value of velocity, which is in which at the leading edge for SU2, and this again probably is due to the fact that the wave pressure is computed between the two software was a bit different. Uh, while in SU2 with coordinate arbitrary compressibility method is used, and open form semi-discretizing momentum equation method is used, and also based on the boundary conditions. Uh, Here on SU2 is for this current case is just far field and airfoil, while Openfoam gives inlet, outlet, and so on. These minor variations might lead to such a marginally higher value in SU2. Although the counting lines for both the software quite similar, except maybe the although the density is similar, the variation of the contour lines along the leading and trailing edge slightly different, and that's the only difference that we can realize from these contour lines. A thin trail at the trailing edge can be observed, and the flow velocity around the leading edge increased as angle of attack increased. So the velocity as told the difference in the velocity increased as the angle of attack went up to 9 degree. As you can see here, the difference is about uh, 4 to 6 meter per second at the leading edge, but there are no other significant differences. So, in case of pressure contours, the difference observed was in the upper limit, where about the difference was about 100. While also in the lower limit, the difference was observed as the angle of attack increased, and this again is can be attributed to the way it was computed, as the other conditions in case Reynolds number, coordinates, and mesh example were all kept similar. Here we can see the contour lines for 5 degree and 9 degree, and we can see their formation of trailing edge vortex, no, an open form for 5 degree angle of attack, and this was separated as the angle of attack increased and the vortex was shed, as you can observe in the angle of 9 degree angle of attack. While the 9 degree angle of attack crossed along the trailing edge, you can see the contour formation uh, have a contour leading to a boundary layer thick, thickness, and this formation was observed prominently on Openfoam compared to SU2. These are the streamlines for static case, so for -5 and 0. The difference again lies in the values, but not in the formation of streamlines and the movement of streamlines along the airfoil. So the streamlines at 5 and 9 degree angle of attack is shown here, and again apart from the highest value for the velocity, there are um, significantly just minor changes observed uh, in case of around the airfoil streamlines. So the flow coefficients were plotted for both the software, which is coefficient of lift and coefficient of drag for different angle of attack, and they both seem to have a reasonable variation and seem to have good agreement. Although as the angle of attack increases, there is a difference between Openfoam and SU2 when in the lift coefficient values. So this difference again is basically because of the difference in the pressure observed. So this pressure, the difference in the upper and lower surface of the pressure, led to the change in CL. Here, a coefficient of pressure shown for selective angles. The difference is as the angle of attack increased, we could see that the formation of leading edge vortex started earlier on Openfoam compared to SU2, and even the trailing edge vortex started the onset of trailing edge vortex and wake started earlier. Uh, this lead to such a variation, but minor variation in CP for as the angle of attack increase. Although with the angle of attack is quite less, the variation is marginally different and it's not significantly different.
Dynamic analysis was done for pitching cycles for angles varying from -9 to +9 angle over a course of 5 complete cycles. The results presented in the further slides have been derived from the 5th complete cycle. Velocity and pressure contours as well as streamlines have been plotted for angles, namely -5, 0, +5 and +9. Coming to the velocity contour, in the case of SU2, it is observed that the velocity contours are similar to those observed for the static cases. This is in accordance with the quasi-steady nature of the flow. The flow is observed to be attached throughout the airfoil surface, and no indication of boundary layer turbulence or vortices being formed is observed in the case of SU2. However, for the case of Openfoam, the trailing edge vortices are observed at -5 degrees. As the angle increases during the pitching motion of the airfoil, these vortices eventually die out and no such disturbances in the boundary layer region or trailing edge vortices are observed for 0 degrees. However, as the pitching angle increases beyond 0 degrees, the vortices begin to reappear at 5 degrees for in the case of open foam. As the angle increases further, these vortices grow and form fully developed trailing edge vortices, which are further shed downstream, as can be seen in the plot on the bottom right corner for 9 degrees. Coming to the pressure contour, in the case of SCO2 results, the results match with the static case. A low pressure zone is develops on the lower surface and a high pressure zone on the upper surface for negative angles. As the angle increases to the positive range, this reverses. For the case of open foam, a similar trend is observed that negative 5 degrees angle of attack, the trailing edge vortices develop, which eventually die out as the angle reaches near zero and begin to reappear as the angle is increased to positive 5. For the prominent low pressure zones, as the angle keeps increasing up to 9. Moving on to the streamlines observed for both SU2 and open foam, it is seen that streamlines are free of any indication of turbulence in the case of SU2 for all angles varying from -9 to +9. However, for open foam, the streamlines show a tendency for circulation at -5 degrees. As the angle increases, the streamlines in SU2 do not still exhibit any circulation, whereas in the case of open foam, streamlines are seen to undergo quite significant deviations. This implies that the flow is turbulent and unsteady, as was observed in the velocity contours. The trailing edge vortices that were formed for higher angles lead to the deviation of streamlines. Coming to the drag coefficient results, it is observed that the nature of CD curve for the dynamic as well as the static case for SU2 are similar. Minor fluctuations are observed during the first cycle, but these fluctuations subside in the further cycles and form a smooth periodic pattern as the flow develops over time. In comparison, the open foam curve for the drag coefficient shows significant fluctuations, particularly for the negative range of angles. Moreover, the maximum value of drag that is observed for open foam is seen to be around 0.18, which is around 0.16 times more than the maximum value observed in SU2. This significant increase in drag can be attributed to the presence of extensive turbulence in the case of open foam, which in turn leads to the increased pressure drag. Moving on to the coefficient of lift results, it is seen that the CL curve for SU2 is linear and is perfectly coinciding the CL curve for the static results. There is no hysteresis observed, and the flow and the CL curve is observed to be perfectly periodic in nature. This linear nature and this coincidence with the static results is due to the fact that the pitching is very slow and hence the flow is effectively quasi-steady. In comparison, open foam curve for lift coefficient is seen to have fluctuations. The possible reasons for these fluctuations have been discussed in the later slides. However, in the case of open foam, the minimum and maximum values of lift coefficient, which are observed for -9 and +9 angles respectively, are observed to be in good agreement with the values from SU2. No sign of dynamic stall is observed in either case, either for SU2 or open foam. As the simulation on SU2 is a multi-cycle simulation, it is observed that the periodic pattern develops as the flow progresses over time. In the case of pressure coefficient, if we compare the static and the dynamic results for SU2, we find that the nature of curves are very similar. This is, however, in contrast with the open foam results. The CP curve for the open foam for the levered surface is always seen to be relatively very flat in comparison to that from SU2. This can be attributed to the extensive development of boundary layer turbulence and the presence of wakes and vortices. We also observed that the values of the minimum CP in the entire flow domain is lower for SU2, that is, it is more negative for SU2. This can be explained in the following manner. The presence of turbulence in any given flow leads to a dissipation of energy. This dissipation of energy reduces the range of pressure values observed in the domain. The CP minimum is observed lower for SU2 which and the difference increases. The difference is seen to increase as the angle of attack increases. The following table shows the different coefficients, the lift coefficient and the CP minimum values for both the softwares for angles -2, +5, and +9. In conclusion, we explored the differences between the two softwares, between the results from the two softwares, and some possible explanations that might have caused the differences. To begin with, we observed that the nature of pitching, as the nature of pitching was quasi-steady, the static and dynamic results were observed to have a good resemblance. The flow and flow parameters quickly developed a steady periodic pattern over the course of a few cycles. However, the major difference that was observed between SU2 and Openfoam was in the drag coefficient values, as the drag coefficient was observed to be 0.16 higher than the maximum value observed in SU2. There were also fluctuations observed in the drag coefficient and lift coefficient curves for Openfoam. These differences can be attributed to various factors like the extensive presence of boundary layer turbulence and the development of vortices in case of Openfoam, which were missing in the case of SU2. Another possible reason could be the difference in grid resolution in the grids used in both the software. As the Openfoam simulation was performed only on the first pitching cycle, the flow is suspected to be transient, and further analysis is aimed to be performed on a large number of cycles to reduce the values of flow coefficients and have a better agreement with the SU2 results. In the work aimed to be done in the future, we aim to explore the differences between the dynamic results and the cause of the differences in association with the respective modeling techniques of the two softwares, as well as the solver algorithms. An experimental validation is also planned to be conducted in the future that should be aimed at providing better insights on the flow physics involved in the low frequency pitching motion. Thank you.